This is a repeated webinar that I have already given approximately a month ago. It's part of the NanoFrazor technology series, and namely, I would like to talk with you about 3D lithography and closed loop lithography, which is a unique feature of the NanoFrazor. So at first, I want to give a short recap on the general technology of the NanoFrazor, most importantly, the thermal probes that we are using, and also a quick recap of the 3D patterning capability of the machine. And then I want to give a few application examples of 3D patterning. And then I want to dive a bit deeper into the new feedback algorithm that we implemented on the machine and which will be soon made available to our customers for using. And I will explain the physical model behind our force actuation scheme, and then explain the model and some corrections, like the so-called Bowing effect, as we call it. And then I will also give a quick outlook. But let's jump right in. Those are the thermal cantilevers that we use for the NanoFrazor. The ones of you that have also been in other webinars probably have seen that before. And our cantilevers are made of silicon, which is mostly degenerately doped. So it mostly conducts like a metal. But then we have one section of the cantilever structure just underneath a very sharp tip, which is not as highly doped. And so it is like an integrated resistor into this electrically metallic behaving structure, or almost metallically behaving structure. And this resistor allows us to make use of the Joule effect and heat the tip up. And this is what we use for writing, this heated tip. And the tip can be very sharp. The radius that has been observed can be down to 2 nanometers or less. Here you see a TEM image. And as I said, we can heat up the tip and write into a resist, or we can convert material. But for the 3D patterning, the most important mode of writing is removal. So you can think of it like a nano milling machine. We remove material. It's subtractive manufacturing, if you want. And for 3D, most importantly, the polymer PPA, which we call our gold standard resist. And we can control the force with which we pull the tip in, and thereby we can achieve 3D patterning, just like a milling machine, really, for the nanoscale. The heater has a very small time constant because it is so small that we can turn it on and off in a few microseconds and really heat it from room temperature to 1000 degrees Celsius and back in just a few microseconds. And then there's also a second resistor that I didn't mention before, integrated into the cantilever structure, into one of the legs. And this serves as an integrated heater/sensor for the topography. Namely, when you get closer with this heater to the sample surface, you reduce the thermal resistance between this heater and the sample surface, and then you increase the heat flux, and this heater will change its temperature slightly, which you can detect by detecting the change of the resistance, which is temperature dependent. And this integrated sensor allows us to have a topography feedback with an accuracy of less than a nanometer, down to 0.1 nanometers. So imagine you are scanning and then you go into a pocket, your heater/sensor gets closer to the surface, and we can detect that. And we can calibrate this signal dependence on the distance to the sample surface by just doing a calibration curve, just approaching the tip with the piezo scanner, and then fitting a model, and then we can get to these very precise numbers of less than a nanometer. And this allows us to do one thing that is special in our patterning approach. We can write on the trace and then have AFM reading of the result on the read trace. So we have immediate feedback of what we have actually written. And this is, of course, very interesting because it means that we can improve while we write, and we can learn, and we can have a closed feedback loop. So you can imagine it like this. We have a certain idea of our writing parameters, then we heat up our writer, and then we start patterning on the trace, and then we quickly cool down our tip, which we can do in a few microseconds, and then we do an AFM scan of the line that we have written, and then we can use that to improve our parameters, and then it goes around, and we will converge towards something that is in the theoretical limitations of the accuracy. And this is all automatic. I will talk about the mathematics behind that. But just so you know, if you use the machine, it will just automatically learn the parameters for you and optimize your patterning. So you don't need to understand all the details. It's just because it's interesting, and maybe you find it interesting as well. Yeah, and then it also gives you other capabilities, not only this optimization of the patterning parameters, but also you can, for instance, stitch multiple patterns together, or what is very important, you can find the devices, for instance, that you want to contact, and then you can exactly make your overlay of the next layer where you want to have it. So you don't need markers or anything. If you compare that to eBeam, in eBeam you would first write in a vacuum environment, and then you would take out your exposed sample, and then you would make a development, and then you would go to some metrology tool like an SEM or an AFM, and then you would check that what you have written is actually what you wanted to write, and then potentially you have to adjust your parameters. So this is all not done in one single tool, and especially not line by line, so you have a much longer loop for the optimization of your patterning. Here are some examples. For instance, holograms have been demonstrated, and there was also a webinar on that. I think it will also be repeated by my colleague Taro. Then you can make electron optics faceplates in silicon nitride that are also 3D patterns. Nolan has given a very good talk, in my opinion, about the optical Fourier surfaces. I think it will be repeated as well. Maybe you could check it out. And then yesterday we had a webinar on the particle self-assembly and Brownian motors, also a very cool application in my opinion. And you can also use it for biological applications, like here this example is for stem cell research. And then another demo that we had is that you can make these optical molecules that show some coupling depending on the distance between them. And for that you also need 3D patterning capabilities. You need to make these dimples in an exact shape. So I promised you some physical modeling, and here we go. So when you look at our cantilever structure, it is essentially a capacitor. We have this large platform structure of the cantilever, and then this is a distance away that we call d from the sample surface. We have some height at which the tip is flying over the surface. When we don't apply any force, we call that Z0 here. That's about 300 nanometers. The tip is about 700 nanometers long, so this distance d here is about a micron. And then we can apply a voltage between the two, and then you will get an electrical force that pulls the cantilever towards the surface. And that depends on the voltage squared and some effective electrical permittivity inside this capacitor structure, and obviously the area of the capacitor and the distance here. And then this cantilever is elastic, and it has a spring constant. So you can really describe it very well with just Hooke's law. And when you take it out of equilibrium mechanically, then you will also have this restoring spring force. And then when you equate both, you get this equation that is in the box down here, which looks very simple at first, but already there it's third order in the distance, and therefore already quite complex. So you can make a simplification, which anyway is very fits very well together with our calibration, which works in the following way. You would just ramp up the force voltage and you monitor the sensor that you have on your writer resistive element, and at some point you will detect a snap-in when the tip touches the sample surface. And this gives you like a reference point, how much force voltage you need to apply to pull the tip in. And then you can analyze this a bit, and you can extract certain parameters, like something that we call a force coefficient, which is mainly the curvature of this parabola. And then also when you heat up the cantilever, it will bend slightly. And this is an effect that we need to consider. So you see some thermal bending of the cantilever, and you can also get it from this measurement if you perform it at different writer temperatures. And then you also see a shift of the parabola. And that's all the parameters that we need. I don't want to go too much into the details, but this is how we can calibrate our model. And then we can develop our model close to this touching point where we have done our calibration. And then we end up with something that looks more simple. We just have, this is basically how deep the tip penetrates into the resist, which is exactly what we are interested in. And on the other side, we have our force coefficient that we get from the calibration and the voltage squared. And then you also have to consider another effect, namely we turn on this force voltage very quickly, and the whole system is dynamic. It goes so fast that we will see some dynamic overshoot of the cantilever. And we also have to include that with a factor that we call R. And because the quality factor of the cantilever is relatively high, this factor is almost 2. So we overshoot almost as much as we would deflect statically when we apply our force voltage. Then we also have to add our thermal bending effect that we get from the calibration. And then as soon as we really start hitting the surface, we lose some energy that is dissipated. And for this reason, we also include another factor that we just call M. It's always less than 1. And that's sort of also the writing efficiency of our tip. And then this is our final model. As you can see, it's rather simple. We just have a distance offset, or basically a starting height. And then we have effective force coefficient times the force voltage. And this predicts for us how deep we would write into the resist when we apply a certain voltage. If you want to have it even more abstract, you could say that the model has only 2 parameters, an offset and a coefficient before the V squared. And now if we want to write a certain target depth, that I denote here with ZT. So this is our model. The written depth depends on the voltage squared and these 2 numbers. And now we plug in a target depth and we solve for the voltage that we need to apply. Then we need a certain idea what these 2 physical parameters of the system are. And our current best estimate is what I denote with a tilde. And then we use a mathematical framework that is called a Kalman controller, which tries to estimate these 2 parameters based on observations that we make as good as is possible with all the information that we have. So it's sort of a statistical framework. We have always some uncertainties associated with our estimates and with our measurements, and it tries to use the best it can get out of this information and the associated uncertainties to optimize our estimates as good as possible. And the observation that we make is very simple. We just make a plot of what we have actually written and of what we wanted to write, so written versus target, and then we make a linear fit. And then we get an offset and a slope, and this offset should ideally be 0, and the slope should ideally be 1. And then we use this observation to optimize our model, and then we do the next iteration, and so on and so forth. So here's how the loop looks like. We make a prediction for the target levels that we want to write. Then we heat up our tip, we write a line, we cool down our tip, we read a line, and then we make our observation fit. We make a plot, what we wanted to write versus what we have actually written. We use this to optimize our current estimate, and then we go to the next line, and then it goes on, and we get better and better. This is what it looks like in the software. So I will make a few demos now, so to say. This is the force calibration that you can run in the software, and then it will find for you the relevant parameters, like this force coefficient in front of the v squared, the thermal bending that you can expect, and also the shift of the parabola. And I want to mention one thing. You can do this if you are working with a cantilever that you don't know yet from a certain batch, and then you will get a set of parameters. But if you use a cantilever from the same batch that has very similar parameters, you essentially don't have to do this again, because the result will be quite similar. And also, the control loop will anyways optimize the parameters for you much better than this calibration can do. Also here we have to extrapolate to the actual writing temperature, which is 1000 degrees or so, because when we make the writer too hot, we cannot take this measurement anymore because we start melting the resist. So we have to extrapolate, so it's only so accurate. But it gives you a first estimate of your parameters, and then you can just write a test pattern for the learning of your parameters. So here's an example how you can do that. That's the sort of the workflow. We want to write a sine wave pattern. There's like a 2D sine wave. Here you can see the target pattern, and then we run the patterning. And at first we calibrate our reader that I have explained earlier. So we do this piezo scanner approach. We fit our model, and now we have calibrated our AFM sensor for the topography. And now the patterning starts from the force calibration that I have just shown. And as you can see in the beginning, we are not writing deep enough. We are not applying enough force, but then the machine learns the right set of parameters. And after a few iterations, we already reproduce the sine wave quite accurately. And then from there on, it just gets better and better until we are completely converged. And at this point, you could actually go and just stop the patterning. And then the machine will remember the parameter that it has found, that it has optimized. And when you start the next pattern, we will already jump in with parameters that are really good. And the pattern will be very accurate from the start. So here you can see a map for the force voltage that has been predicted for a certain target depth. And in the beginning, the force voltages were not high enough, and then they converge towards something stable. And another analytic feature that the software has is that you can look at this observation fit that I have explained previously. So we see here the measured depth versus the target depth. In the beginning, we were not writing deep enough. We were not applying enough force. So we are sort of clipped here towards 0. But then after a few iterations, you can see how the machine learns, finds a more adequate set of parameters, and then we reproduce measured with this target super accurately with a slope that is 1 and with an offset that is 0. So now we have learned a set of parameters. We have aborted the patterning, and now we want to go for the really good pattern just from the start. And as you can see, we jump in with our previously learned parameters. Now we don't have this offset in the beginning, and after 3 iterations, we are already very accurate. In the beginning, there was a little bit of adjustment necessary, but now we are already quite good. And I will let this run in the background and come to another effect that we need to take care of. And we call this effect the bowing effect internally. So the issue is the following. When you write a pattern into the resist, then you change this effective permittivity in between the capacitor, because the resist has a different electrical permittivity than the air. And when you remove some resist under the cantilever structure, then you will change this effective permittivity and thereby the capacitance and thereby the force coefficient of the model. And this is not so easy to predict and to calculate, but we can similarly as the parameter finding also learn what this bowing effect is, and then we can correct for that. Also here, I don't want to show too many details, but you can imagine it like that. Suddenly the capacitance of the cantilever structure becomes a function of the location on the sample, because we have already a pattern underneath. And that means that also this force coefficient becomes is modulated the same way. And that means that our S1 parameter of the model suddenly is a function of X and Y. And we have to extend our model in the following way, where we include also again the actual modulation that we can basically never know, and then also our best estimate of this modulation. And then we can in the same way let the machine learn for us what this bowing correction, as we call it, is. And if you don't do that, it's actually quite annoying. Even if you have completely converged physical parameters S0 and S1, you will still see some residuals of the written versus target, which are now not a function of written versus target space, but they are a function of X and Y. And here you can see two examples that we patterned, where you see that the pattern bows up in the center and then bows down towards the edges. And without the correction, it's not really possible to write completely accurately what you wanted to reproduce. Here's another example of the sine wave pattern that I have shown you in the demo. And here I don't have this bowing correction, and I also provoked a case where this is most severe by positioning the cantilever in the worst way possible. And then you see that the pattern is severely degraded towards the edges. So the whole thing is really bowing down. We are writing too deep on one edge. And we analyzed this a bit, and we made some simulations. And the first result that we estimated was that actually the force voltage that you need to apply to really reproduce the sine wave, for instance, has a modulation on top that is on the order of the modulation that you need to apply to write your pattern. So this is actually really important. Here is what I let run in the background. And our pattern is now finished, right? You remember we started with our already learned parameters. Pattern is now finished. Sine wave looks quite nice. And what I didn't tell you is that this correction, this bowing correction, was all the time already activated. So what you see here is the good case, where we have the correction algorithm for the bowing effect activated. And I can quickly show you. So when we go into our analytics tab, we can see a map of the voltage correction that was applied on our force voltage. And you can see that just as expected, we needed to do some corrections, especially towards the edges, and especially when we have already written a lot of the area. Because as you can imagine, the more pattern we write, the more we change the capacitance and the more severe the effect gets. But we have corrected that. And as you could see, the result was rather good. Now, when we try to write the same pattern without the bowing correction, so it is now turned off, you can see that we end up with the bad example that I have shown before, where I really provoked a lot of bowing. We cannot really accurately reproduce the pattern that we want to write without the correction. But don't worry, if you activate the correction in the software, the machine will learn also this bowing effect for you and correct it accordingly. Here you see a comparison. This is the pattern that we write without the correction, and on the right you see it with the correction, and then it is actually reproduced as good as the machine can, essentially, with its intrinsic noise. I also promised you an outlook. So we want to extend our cantilevers with a backside electrode, and prototypes already exist. And the advantage of that is that you don't need a conducting sample anymore. So you can also pattern on insulating samples, because now you can modulate your cantilever with this backside electrode, which again is like a capacitive structure on the backside this time. And also this allows us to do one more thing, namely we can also modulate multiple cantilevers individually. And this, of course, is very nice, because it can either give you a full rack of cantilevers, so you don't have to change your chip so often, and you can also save a lot of silicon area, so you can create many chips with potentially reduced cost. And also in the future, we could use this to write in parallel with multiple cantilevers at the same time to enhance the throughput. And this is a very interesting project that we are working on at the moment. Okay, so I thank you for your attention.